Okay. Hello, everybody. I hope everyone's having a wonderful day. So today we're going to be talking about smoothness. Now, before we can actually talk about what a smooth function is, I need to give you some setup so we can actually make it in precise statements about what exactly we want to accomplish. So first, I want to remind you, if you're not familiar with this definition, don't worry, we're going to talk about it. The concept of an asymptotically non-decreasing function. So an asymptotically non-decreasing function, sometimes people call this eventually non-decreasing. I like that name too because it's very intuitive once you see the definition. You're going to see that this is it'll feel of a very similar flavor to the big O definition that we've been working with for a while now. So many functions that, just because I want to be upfront about this, that many of the complexity functions that people study in computer science tend to be asymptotically non-decreasing. So when you formulate a complexity function, it's almost always, with some exceptions, of course. I'm not going to talk too much about those exceptions yet, because I'll talk more about this. I'm going to dedicate proper time to this topic in the future, or at least in another video. Where we're going to talk about, I'm going to take the presumption that we know that these functions are all asymptotically non-decreasing or eventually non-decreasing. So just to be clear, this definition will apply to almost all the complexity functions you're going to encounter in typical study. So what do I mean by asymptotically non-decreasing? So we call a complexity function asymptotically non-decreasing if and only if there exists a positive integer n0 such that for all n greater or equal to that n0, it must be that f of n, so if I'm talking about function f, where's my marker? F. So if I'm talking about function f, I know that f of n is less than or equal to f of n plus 1, all points after n0. So it can be at n0 or after. So just to give you a picture of what I mean, so a function might look something like, this. A function might look something more like a parabola. It might look something like this. But a function also, so we can also have functions that look something like this. All of these are examples of asymptotically non-decreasing functions. Why? Because first, I haven't told you what each of these are. This is just meant to be a picture to help give you the intuition of or strategy of how you would prove a function is asymptotically non-decreasing. So, for example, remember n0 in this case is a positive integer, so you can't just simply assume it's here. It has to be somewhere this direction. So for example, I could select n0 to be right about here. And notice that if I look anywhere to the right of n0 or on n0, if I plug in n, does the function always go up or stay level? If that's the case, then we're okay with this point at n0 here. So if n0 and on, so everywhere after n0, it's either level or it's gotten larger, the quantity, when I insert one higher value, then we're okay. Likewise here, the same thing is true, except everywhere it's going up. So we would call this increasing function. So this is a non-decreasing function. It's not just asymptotically non-decreasing, it is just non-decreasing. But it's also increasing. Increasing meaning that it always gets larger. It doesn't plateau like this. It always goes up. So here I could just select n0. And every one of the n's after this are all going to satisfy the relationship I have there. Remember, they can be equal, but it must be that if I put f of n plus 1 in, it must be larger than f of n. It's either equal or larger, one of the two. Now this one over here, this function h, if I looked at this one right here, you would see quite quickly that it's like, okay, well, look, it has this dip right here. Now I'm just presuming the behavior of the function because I haven't told you what it is. Because it's very real possibility that you could have a function that looks like it oscillates up and down like this, which can be a problem, right? If you're going up and down, up and down, up and down over again, are you going to be able to find n0? You might have difficulties doing that. However, here you'll notice it goes up, then it dips down, then we presume it goes up. So if I were to select, say, n0 just right at the bottom or the trough of this curve right here, if I pick n0 right here, you'll notice that if I were to now check this over, you'd see that, okay, that makes sense. So when you're doing this formally, it would be very similar to when you prove a big O claim, just you'd not have a C. You would just have n0, that's it. But the main point I'm getting at is that you'll notice that it's not like the big O statement exactly, but notice it's one value higher. So all you do is you'd substitute in n with n plus 1 on the right-hand side. We'll do more examples of this in the future, or in another video. I'm not going to focus much on here because almost every function you're going to encounter has this property, at least in your typical study of computer science. Not all of them, but definitely ones that you'll encounter if you were to generate a complexity function based on analyzing an algorithm. That's typically what you'll encounter. So I want you just to keep in mind that asymptotically non-decreasing is a property that many complexity functions have. Constant, logarithmic, polynomial, and exponential functions all are asymptotically non-decreasing. So where are we going to go with this? Now, that's one piece of the puzzle of what I want to talk about today. So the other thing is talking about a concept called smooth, which hence the title of this lecture is called smoothness. So often when we talk about complexity functions, many of the ones that we encounter have so-called smooth behavior. So I'll give you a sense of what I mean by that word, because there's different ways we can talk about the concept of smoothness when we talk about functions. I'm going to talk about it in the following sense. So I mean it when I'm able to restrict the inputs to some subset of values such that I'm talking about the entire domain. So I'm talking about, like, okay, when, for example, n is equal to some power of b. So for example, if b was 2, then we're talking about all the when n is a power of 2, like it's 1, 2, 4, 8, 16, 32, 64. So what I want to do is I want to have it so I can able to look at simpler cases like this, but I still want to make general statements about its overall behavior for any n. So if a function is so-called smooth, I want to be able to do the following. So imagine I give you so the goal will be I'm studying asymptotically non-decreasing functions. Say f is one of these. My goal is if I know f is big O of g, when n is, say for example, n is a power of b, I want to be able to have some simple set of conditions that allow me to say that if this is true for these sets of values, for these particular n, I want to be able to say something about the overall unconditional asymptotic behavior of the function for all n. So I want to be able to give you very simple conditions that allow you to make simple assumptions about the input. Because very often when we talk about different algorithms, their behavior is easier to analyze for certain inputs as opposed to general inputs. So for example, it might involve rounding up and down for certain values of n. This type of assumption is very useful when we start talking about so-called divide and conquer algorithms, where you have the input and you split it in halves. So for example, if the input is even or odd, it changes how divisibility works when it comes to rounding up or down the input. When we actually start generating a complexity function we want to actually analyze. So when you make presumptions about the input, those complexity functions that we derive from analyzing the algorithm itself are easier to analyze mathematically when you make certain input assumptions. So I'm not talking about the general input of the algorithm. I'm talking about assumptions I make about for my complexity function itself. So I want to be able to say, so I have this overall algorithm analysis I did. Now I want to consider it for only certain values of n. So like when n's a power of 2, which is very common with algorithms of the nature I just described. Things like binary search and merge sort have analyses that are very simple to do when you assume n is a power of 2. At least it's simpler. I'll show you an example of one where I gave you a tougher analysis earlier on, but I'll show you how you can use this idea to simplify it quite a bit. So in that case, what I would be doing is looking at the function I analyzed, and now I want to consider a subset of the input. So like this, where n is a power of b. And then what I want to do is I want to be able to say something about f in relation to g asymptotically. So that's going to be our goal. So this property of so-called smooth function plays a big role in this. So I want to write down the definition of smooth. So a smooth function. So a complexity function. A complexity function f of n. So we say that a function is smooth if it satisfies two properties. That one is asymptotically non-decreasing. So that's the first piece I talked about earlier. So it's asymptotically non-decreasing. That's the first thing it has to satisfy. The function has to be asymptotically non-decreasing. And two, it must be that f of 2n is big O of f of n. So this definition's the one you want to keep in mind when we're talking about smoothness. So what do I mean by this? So the first thing, just observe that what this means. So this means that remember, when I prove a big O statement, I'm talking about I need to find two constants, c and n0. C is a positive real number, n0 is a positive integer, such that f, whatever the original, this guy is, so f of 2n, so it would be f of 2n is less than or equal to c times f of n. And this has to be true for all n greater or equal to n0. So notice there isn't an f and a g, but you're going to look like this as f and this is g. That's how you would prove claims like this. We're going to see some examples in another time here. So you might ask, what kind of functions are so-called smooth functions? So some examples of smooth functions include constant functions, such as, like, if I just gave you some constant d. So it's like f of n is equal to d. Logarithmic functions like log base 2 of n, these are also smooth. Polynomial functions like n to the k, where k is some constant greater or equal to 1. These are all examples of smooth functions. However, you'll notice that I've listed essentially the same list I had for asymptotically non-decreasing. Do you see one that's missing? Is there any one of these? Is there any one that's missing from my list I had earlier? Yeah, there was one, right? So some functions are not smooth. So for example, if I give you 2 to the power of n, so so-called exponential functions. So these are not smooth. So just be warned that not every function you're going to encounter is smooth. However, I said that most you're going to encounter, or many of the ones you're going to encounter, are going to be asymptotically non-decreasing. That's an important thing to note of. So proving smoothness is proving two things. The function is asymptotically non-decreasing. Is asymptotically non-decreasing, and you're going to prove a big O claim. Now, for anybody that is up and ahead of big O, it's worth noting that everything I'm talking about in terms of smoothness for big O applies to other asymptotic notations such as big theta or big omega. I haven't talked about those here quite yet, but I should point that out. So anywhere I'm saying big O, you can put in other asymptotic notations you might be familiar with. So big theta would also be 1. There's actually a much stronger property that comes out of knowing a function is smooth. So knowing a function is smooth, guarantees a stronger property and it says that all smooth functions are B-smooth. So all smooth functions are what we call B-smooth. So this is a stronger condition. Because remember, I wanted to give you a set of very simple conditions that you can prove. Like I said, proving smoothness, it doesn't look, actually, it's not that scary looking. It's just really a big O claim. And depending on your audience, they might be familiar with your function being asymptotically non-decreasing. So really, if you know how to prove a big O claim, you're not really that far off. And it's a particularly easy condition to prove, as we're going to see in some examples. So let me define what B-smooth is. So this is going to be a complexity function f that is both this might look familiar, by the way, that is both asymptotically non-decreasing. So that's no different than the smooth definition. What is going to differ is the second condition here, that f of Bn is big O of f of n. So I'm just going to number these just to not confuse anybody thinking that's a negative sign. So you have to show that f of Bn is big O of f of n for every integer constant b greater or equal to 2. So that's a 2 over there. So it's a b greater than or equal to 2. So there's two conditions. It's asymptotically non-decreasing, and for any integer constant b greater or equal to 2. So remember, this is a universal statement. So it's saying for every integer constant b. So if I just fix you b, so it has to work for any b. So it has to be f of Bn is big O of f of n. This is where they differ, because remember, the definition of smooth is just that the b is 2. So an important theorem that I want to point out that's used in one of the more sophisticated proofs that I'm going to show you is that if complexity function f is smooth, then f is B-smooth. So any smooth function is B-smooth. That's one of the important things I want you to observe, is that if I just prove smoothness, I get B-smoothness for free. And this property of B-smoothness comes up in one of the proofs that I'm going to show you later on. Kind of what the main one I would show you. So the proof that I'm going to use here uses mathematical induction. I'll be doing that in a separate video from this one, just because like I said, I want to keep things on the same course so you can see what we're going to use this for. So this is for much more of a doer. So if somebody really just wants to use smoothness, we're in the right spot here, okay? So just keep in mind, smooth means be smooth. So that's one lovely property that we do actually have. So that brings me to talking about what some people call the smoothness rule. So this is the main ingredient that I want you to be aware of. So here's a theorem. So some people like to call this the smoothness rule. Now, you can actually show that there's other kinds of so-called smoothness rules, but I'm going to show you this one because this is a very common one that comes up. So I'm going to say, let there be two complexity functions functions f and g. I need a comma. Don't forget your commas, it's very important. Where f is in big O of g, when n is a power of an integer constant b greater or equal to 2. Now, so far, this should sound familiar to what I showed you at the beginning. So I want to have it where I'm able to make some simplification of the input. I consider a restricted case, such as this one. So where n is a power of b. Now I'm going to show you the very simple conditions that you need to get it so that you could just say things about the general complexity function for all n greater or equal to 1. So just unconditionally. So like I said, the concept of smoothness is that I can make restricted assumptions about the input, and because of the smoothness of the function, that assumption will propagate across all of the inputs. So normally when you actually take and do the general analysis, normally involves rounding up and down numbers and things like that. This will allow you to get away without having to do any of that stuff. It's really nice. So now here it is. This is all you have to do. So if f is asymptotically non-decreasing, and g is smooth, then f is big O of g. So let me dissect the smoothness rule here for you. So I have two complexity functions, f and g. F just needs to be asymptotically non-decreasing. As long as g is smooth, so if you know these two facts, remember g is already asymptotically non-decreasing because that's part of the definition of being smooth. So if both of these are asymptotically non-decreasing, and all you have to do is really prove that second condition of smooth, then you get unconditionally that f is big O of g, regardless of what n is. So it's across the entire domain, which it would be n greater or equal to 1 most times. So whatever the valid domain is for what n is. So this is something that allows you to make a lot more simplifying assumptions. So the proof for this invokes using the B smoothness property. I'm not going to talk about so much that here. I'm going to do that again in a separate video. And now, if you make the presumptions about this theorem, the big reason why you can do this is, now I want to remind you what I said at the beginning. So if n is like b to the k, and I show you that like f of n is big O of g, all this is really saying is if you assume both of these, in particular where it's asymptotically non-decreasing, as long as g is smooth, then you can just simply say f of n is big O of g of n. You don't need these quantifiers on n, and you don't need the fact that like there's no assumptions on the input here. That's the big thing I want you to notice. Now I make a bold statement, I could say it about the entire domain of the inputs for my complexity function. Is that clear to everybody? So that's the main motivation of why we can use this smoothness rule. Like I said, there's other ones that do exist. For example, in my notes, I have an alternate proof for the smoothness rule where instead of assuming n is a power of b, n is a multiplicative or a multiplicative factor of a number like b. Or in other words, it's a multiple of b. So that's another assumption that might be very handy. So do exist several different proofs for this one, and the one that I uses B smoothness, and that proof is very easy to generalize to cases like that. The reason why I wanted to show you this is that very often in computer science courses, you'll find that the professor tends to make assumptions that look just like this one, but never really explains to you that you can make these assumptions. And it still say things about the general properties of the analysis. So this happens very often in algorithms courses when they don't really have time to talk about this. So sometimes people get to see it. Let me know in the comments or wherever you might be watching this if you've encountered this in one of your classes. This is something handy to know. So I want to dedicate the last bit of time I have here talking about harmonic numbers. Now, last time we talked about harmonic numbers. And I did an analysis showing that the harmonic, if I give you the nth harmonic number, I know it's big O of what? It was big O of log n. So it has a logarithmic asymptotic behavior. So what I would like to do is I would like to use the concept of smoothness to give you actually a simpler version of that proof. Because that proof actually, I did a lot of little setup here and there, and it wasn't really, I wouldn't call it elegant because I had to do a bunch of setup. Now keep in mind the definition of elegance, there's no concrete definition I'm going to use. But the point is that if you remember that video, it was pretty long and exhaustive where I had to like say, oh, n is a power of, like I rounded up to the next power. I do this, all this sort of stuff like that. And it's not, if you really are savvy with analysis, you would follow through with it, no problems. However, there's sort of this problem where like, it seems like I'm doing a lot of artificial work for the analysis, and I would like to be able to just talk about instead just a power of b rather than having to round up to 1. You'll see what I mean when I get to the analysis. So I'm going to show you an example of me using the smoothness rule. So here's an example. So I'm going to be revisiting harmonic numbers. So now, if you haven't seen that video, I'm going to define what a harmonic number is. So recall that, that a harmonic number, which I'll call h of n, like a function. I'll use functional notation, but oftentimes people will use h of n like this, where n is a subscript. The nth harmonic number for an integer n greater or equal to 1 is defined as follows. So it is, you would start off with 1 plus 1/2 plus 1/3 plus 1/4 and so on until 1 over n. So this is whatever this is, that is the nth harmonic number. So for example, if you're savvy with summation, so I use that in the example, this is equivalent to me writing the sum from I is equal to 1 to n. So the lower limit here is saying I'm starting at 1 and I'm going to finish when I get to n. So h of n is going to be equal to the sum from 1 to n of 1 over I. So for example, h of 1 is what? What is h of 1? H of 1 would just be 1. How about h of 2? What's h of 2? It would be 1 plus 1/2, which is how many? It's 3/2, and so on. So what I'm going to prove for you, because this is about big O claims, I'm going to prove for you that h of n is big O of log base 2 of n. So I want to prove this for you. So I did that in a previous video to this one. I'm going to show you how you can use smoothness to simplify the analysis quite a bit. So it's going to be pretty fun. So let's do this. So the first thing I want you to really observe, and I'm not going to write this in my proof, but I want you to, I must stress that it shouldn't be very hard to see. Now, that is obviously a sloppy level of reasoning, but it shouldn't be very hard from the definition of the nth harmonic number that you should be able to see that h of n is in fact asymptotically non-decreasing. Why? Why? Now this is the more mathematical reasoning that I would like to see. If somebody asked you why is the harmonic series, or the harmonic number, why is this function h, why is this asymptotically non-decreasing? Well, notice that every time I put in a number, like n, it's always going to, it never goes down, right? Like, I've always added more quantity to it whenever I increase n by 1, right? It just goes down by a little bit. So, for example, h of n is, if I put n as 1, it's 1. When h of 2, it's 1 plus 1/2, right? So notice that that's bigger, that's strictly bigger than 1, right? It's, in fact, an increasing function. So it's always going to be increasing. Now, I'm not going to show you the proof how to argue that. I have a very simple explanation in the notes that you can do algebraically. So I'm only going to focus so much on the fact that, that we know that logarithmic functions like that one over there are smooth. So I'm going to use that property. So I'm going to give you a proof. So I'm going to assume n is greater or equal to 1. Assume n greater or equal to 1 is a power of 2. Now this is where it gets very nice. This gets very nice. So if n is a power of 2, you might remember from my analysis I had before that I tried to make sure that I had this other value m, and I tried to round that up to the nearest power of 2 above, right? Like, I want the next power of 2 if it isn't a power of 2. Now, if I make this assumption, this greatly simplifies my analysis in the following way. So if I assume n is a power of 2, then h of n is equal to h of 2 to the power of k. So that's a k over here. So it's h is equal to 2 to the power of k. Let me just get a little bit closer in. So h is a power of 2, right? Sorry, not h. N is a power of 2, right? So now, because we've assumed n is a power of 2, then h can be rewritten like this. H of n is equal to h of 2 to the power of k for some k greater or equal to 1. Actually, we want it to 0, right? Because we also have 1 in here, right? We're talking about powers of 2. What's 2 to the power of 0? It's 1, right? So we need to make sure we include when k is equal to 0. And, now this is the great part. And I can rewrite it like this. H of n is equal to the sum from, I'm just going to use the definition of what a harmonic number is. I is equal to 1 to n, which this is going to all be equal to 1 plus 1/2 plus 1/3 plus 1/4, all the way up to 1 over 2 to the power of k. So this sum right here is h of 2 to the power of k. Do you see how this looks very familiar? This should look very familiar to you from the proof I gave you before, right? So now what we're going to do with this is I'm going to use the exact same strategy I used before. I'm going to develop a second series. I'm going to bound that from above. And you're going to notice very quickly, because I assume n is a power of 2, that this should actually greatly simplify the analysis that I do afterwards as well. Okay. So I'm going to start writing down what we're going to do. So remember, we want to say what we're going to try proving, right? This is just a little setup, because I'm going to invoke the smoothness rule. So we need to find a positive real constant c, right? We need to find c and n0 so that for all n greater or equal to n0, h of n is less than or equal to c times log base 2 of n. Right? So what did I do last time when I tried doing this? I tried to formulate a second series I could bound from I want to bound it from above so that I can say something, so I can chain together something. I end up getting something that looks like a logarithmic term. That's going to be my goal. I want to start off with h of n. I want to bound this from above with the second series, something that's sandwiched in between these two, and then I'm going to try to get a logarithmic term. That's going to be my goal. So I'm going to formulate a second series as follows. So it's worth noting that the second series I'm going to have on the right-hand side of my inequality. You can write this down with summations, but like I said, it gets a little tedious. So I'm going to start off with 1. So I'm going to start off with 1, like I have in the definition. I have 1 is less than or equal to 1. You would agree with me that that's true. 1/2 plus 1/3, that is indeed less than or equal to 1/2 plus 1/2. So if I replace 1/3 with 1/2, you would agree with me that this inequality will be true when I evaluate the two sides, right? How about if I write down 1/4 plus 1/5 plus 1/6 plus 1/7? Well, if I write down, so 1/4 is in fact equal to 1/4. Let's put 1/4 right here. Let's use the same idea. 1/4 is indeed larger than 1/5. Same thing. 1/6 is definitely less than 1/4, and 1/7 is definitely less than 1/4. So what I'm going to do, this is sort of the strategy I have, at least. This is the common strategy you might use with the harmonic series. If you're ever doing more with a harmonic series, this is the common strategy. Is I'm going to write out the number of terms in terms of a power of 2. So I start off with 2 to the power 0, I have 1 term. I have 2 to the power 1, I have 2 terms. 2 squared, I have 4 terms. So the next inequality here should have 8 terms on each side, where I'm going to have it 1/8, 1/9, 1/10, 1/11, and so on. And then all these are going to be replaced with 1/8. So I'm rearranging all the terms of my sum so I can build something. And I'm just going to use my bucketing strategy I showed you in a previous video, where I have one side of the inequality, and I put something that is at least the value that's over on the right-hand side. If I can argue that for each one of the terms, when I put them all together in one bucket on each side, then it must hold as well for the appropriate domain. So if I keep writing this out, you'll end up with, so if I keep going, so I have 1 over to the power k minus 1 plus 1 over to the power k minus 1 plus 1. Note the plus 1 is not a part of the exponent. Plus 1 over to the power k minus 1 minus 1. Should I have the minus 1 here? No. So you notice that the strategy here, notice that every one of these is the next power of 2 is the next term over. So you always have to subtract 1 off. That's how I'm getting the pattern to work, right? So notice here, if I had the next term after 1/3 in my sequence over there, it would be 1/4, right? But 1/4 is right there. Just like here, I have 2 to the power k, which is the next power, but I minus 1 off of it. So you could try this out. Try picking a fixed k and see if it makes sense to you. That's what I recommend if this isn't clear on the first day. So all I'm going to do is just do the same strategy. I write 1 over to the power k minus 1 plus 1 over to the power k minus 1, and so on, plus 1 over to the power k minus 1. But how many times am I writing this out? Well, it's based on the number of the power, right? So how many times does this get written out? This happens 2 to the power k minus 1 times. So that whole thing, that whole sum, it should be 2 to the power k minus 1 terms all being this. Okay? And then I missed one term, right? There's a final term. It's the 2 to the power k term, which is equal to n, right? So now I'm just going to insert that at the very end. 1 over 2 to the power k. You'd agree with me that's in fact equal to it, but I'll just keep along with the inequality. So now I have my second series on the right-hand side. Over there is the original series over there. So what am I going to do? I'm now going to bound it using this relationship. Remember, think of the buckets. That's an easy way of thinking about this. So let's move over to the other board. Let's wrap this thing up. So you're going to see how smoothness makes things much easier for us. No more rounding up and down. Don't have to do any of that stuff. So just to summarize my point. So h of n is equal to h of 2 to the power k, right? That's what we established. It's a power of 2. And then we know that this is going to be less than or equal to my right-hand side. So my second series I have, which is 1 plus 1/2 plus another half, right? That's the second row. The third row, I have 4 1/4, right? And so on, right? And then I have my, what else do I have? I have all those 2 to the power k minus 1s, right? 1 over 2 to the power k minus 1. It's a little small. 1 over 2 to the power k minus 1. We have a bunch of those terms. 1 over 2 to the power k minus 1. Right, we have all of those. And then finally we have the 1 over 2 to the power k, the final term. I think I got everything on this board here. Let's see. Bingo. So this is what the second series looks like if I were trying to write it all in one line without any fancy notation. Now I want you to look very carefully at this, and I want you to see, okay, well, we have 1 here. Okay, what's 1/2 plus 1/2? If I have half a pi and another half a pi, can I fit them both into a pie pan and create a 1 whole pi? Yeah, I can. So notice 1/2 plus 1/2, that's just 1, right? Same thing, if I had 4 quarters, that should make 1 pi, right? Same thing here, if I have 2 to the power k minus 1, and I write that out 2 to the power k minus 1 times, each one of these is a reciprocal, so it's 1 over that. In fact, you can see it over here. What would be 2 to the power k times 1 over 2 to the power k minus 1? Sorry, 2 to the power k minus 1 times 1 over 2 to the power k minus 1. What is that? That's just equal to 1 if you know your algebra. So what happens? What happens here? So what's happening? What's going to happen here? Okay. So what's going to happen? How many times am I writing 1 out? How many times do I do it? Well, let's think about it. The hint I'm going to give you is look at the exponent. So I have k minus 1 here. So I have k minus 1 ones up to this point, plus the first row over there, which that was 2 to the power 0, right? But how many numbers are there from 0 up to k minus 1? Well, it's 0 plus k minus 1. But what is that? That's just k, right? So that's k plus the final term I did not include anywhere else. So that's 1 over 2 to the power k. Boom. There you go. So you're going to see how we're going to use this next. Now, here we go. Now you're going to see why the power of 2 is going to make things much easier now. So I'm going to say observe that for all n greater or equal to 1, that h of n is less than or equal to k plus 1 over 2 to the power k, which is what I wrote up here. Which, what is k? What's k? That's the exponent of some power of 2, right? But what is that? If I write down, if I tell you, okay, 2 to the power of k is something, what is k? What is k? If I wanted to write that down in algebraic terms, what k is? We had a name for this. So if I wanted to know, if I gave you x, So if I give you x, and I know the base of the exponent, what's k? What is that? That's log base 2 of the thing. But what's x here? It's n. Remember, n is equal to this. So n is equal to that. So what does that mean? What's k? That's log base 2 of n. And because n is a power of 2, you know it's never going to be rounding up or rounding down to the nearest integer. It's always log base 2 of n. Because this will always end up being a whole number, because it's the power of 2. So everybody see that? So this just comes from the definition of a logarithm. So now I have log base 2 of n plus 1 over n. Where did n come from? Remember, n is equal to 2 to the power of k, right? So I'm just going to replace that back with n. And you'd agree with me that for any n greater or equal to 1, that 1 over n is less than or equal to 1, right? Because it could be 1 over 1, then it'll be 1/2 plus or a quarter. It could be an eighth. But the point is, it's not going to be exceeding 1. So, boom. Look how much easier that is. So now we're going to pick c. Because now, look at this. Now I have something that says a logarithmic term here. So I'm going to pick c is equal to 2. Then I say what I'm going to do next, right? Then we need to find n0 so that what? So that h of n is less than or equal to c times log base 2 of n. So we're going to pick c to be 2, and I'm going to use the same strategy I did in the original proof I gave you. I'm going to make two terms that look a lot like logarithms. So notice that when n is greater or equal to 2, if you remember that also that I used a different n0 as well in that proof, that h of n is less than or equal to log base 2 of n plus 1. So I'm going to start on the left-hand side. I already know this. And then what I'm going to do is I'm going to try to turn this into so that the 1 is log base 2 of n. So it's less than or equal to log base 2 of n plus log base 2 of n. You know that this is going to be 1 or greater. So this is greater or equal to log base 2 of 2, which is equal to 1. Now, you might ask, Dan, how do you know this? It's because logarithms are also non-decreasing. They're like, we know that these are also asymptotically non-decreasing, but they're also non-decreasing more generally. So my point here is that I'm just going to use this fact. I'm going to replace this with a logarithmic term. But what is that? That's equal to 2 log n, log base 2 of n. And there, we got the right-hand side. Piece of cake. So I'm just going to choose, n0 is equal to 2. The function, so now this is where I'm going to invoke the smoothness rule. The function log base 2 of n is smooth. Therefore, now this is where you could say by the smoothness rule, but I'm not going to do that. I prefer just invoking this property directly. Therefore, h of n is big O of log base 2 of n unconditionally. And we're done. So you'll notice that now there's a lot less artificial stuff in my analysis. When I mean artificial, I mean that I had to derive and add more variables to round things up, well, which are mathematically correct, but they seem to get in the way of the overall argument that I was making, which now you can see it's a much more pure argument now. So I'm just invoking the smoothness to make this much easier for myself. So hopefully that's clear to everybody. So this is one example of me invoking smoothness. Here I use the fact that I assume n is a power of 2. But like I said, These kind of assumptions oftentimes dramatically simplify the analysis so that we don't have to worry about, oh, do I need to round it up to the next power of 2? Do I need to make a variable for that? Or if I make other kinds of smoothness assumptions, such as, oh, if it's a multiple of some number, like a multiple of b as opposed to a power of b. This allows me to make assumptions like, oh, if it's always even, for example, then I can get rid of worrying about, oh, is it going to round up or round down if I want to get a next integer. These things oftentimes are dealt with nicely with smoothness. So that being said, that's all I have to say about smoothness. Thank you very much, and have yourself a beautiful day.